Hi, I'm Grant Pearce. I'm a senior scientist with the Scion Rural Fire Research Group, and I lead the extreme fire program that we'll be talking about today. So I'll just start my presentation. All right, so I'm going to be talking about the extreme fire program. So the extreme fire program is a 5-year program, and we're just currently entering the last year of that program. So we finish in September next year, and we're currently looking at rebidding the program for what might come following the end of this program. But I'd like to talk about 3 aspects of the program today: the extreme fire behaviour research burns, the real-time fire monitoring tools, and the extreme fire prevention sensor technologies. So the program is funded by NBIE, but we receive co-funding from the Forest Growers Levy, from other partners, Fire and Emergency New Zealand, Department of Conservation, and also New Zealand Defence. So the first area I'd like to talk about are the research burns. We're testing a new fire spread theory developed by the US Forest Service's Missoula Fire Sciences Lab, based on a series of lab fire experiments. And those studies have shown that radiation on its own is insufficient to ignite fuels, especially those loosely arranged fine fuels in which fires start and spread. And their theory suggests that convection is much more important than previously thought, and perhaps as important, if not more important, than radiation in transferring that heat ahead of the fire front to the unburned fuels. And convection acts to set up a series of up and down drafts above the fire front, where the heated air rises, but then as it cools, comes back down and pushes down into the flame front, pushing the flames out into the fuels ahead of the fire. So those fuels are then preheated through radiation, but also this convected heat and through direct flame contact. If proven, this new theory could fundamentally change fire science globally. It will change the way we teach fire science and heat transfer to firefighters, and ultimately result in more accurate fire spread prediction models. Then in turn, that will lead to better decisions being made during firefighting operations, and ultimately to safer firefighters and communities. So the study aims to conduct burn experiments in 3 different fuel types: cereal crop stubble, where we conducted burns in 2018 and 2019. Gorse scrub fuels, where we recently completed burns in March this year. And eventually moving into, we hope, standing wilding conifers over the next couple of years of the program. And here we aim to measure these heat transfer characteristics and other fire properties, including fire spread rates, flame lengths and intensities, for example, with the ultimate aim of improving understanding of extreme fire behaviour and fire spread. These research burns are a major international collaboration, and as well as ourselves and the Missoula team, we are also collaborating with the University of Canterbury's Geography Department, the San Jose State University's Fire Weather Research Lab, the University of New South Wales from the fire modelling standpoint, and we've also used the expertise of the Scion UAV team. During these burns, we deploy over $2.5 million of equipment in the form of high-resolution thermal cameras, LiDAR, drones, wind anemometers and other sensors, and each of the collaborators bring some of the specialist equipment and expertise to the program that enables us to do research that we would not otherwise have been able to do here in New Zealand on our own. So the Gorse scrub research burns were just completed in March this year. We completed 6 burn experiments in these more complex, non-uniform scrub fuels. Each time we were burning a 4-hectare research burn block, with 2 burns being conducted per day, with 3 burn days over the 7 days that the research was conducted. But prior to that, we required 3 further days to complete the burnouts to secure the site, to prevent escapes, And the burns involved the 30 research personnel, but more importantly, also the support of over 35 to 40 fire and emergency dock and other staff and suppression equipment. And we're very grateful for that support. So this is some footage from one of our in-fire cameras that shows the flame front approaching. And here you can see that we got extreme fire behaviour as we'd hoped, as the burns burn through the sensor arrays that were deployed within the blocks. Hopefully you can also get a sense for the noise and the heat that's generated through these burns. So looking at some of the results to date, these gorse burns were hot and definitely hotter than the previous stubble burns that we'd experienced. The spread rates were in the order of 3 to 4 kilometres per hour, with all of the burns being over within less than 4 minutes from ignition. Flames in the order of 8 to 10 metres high on average, but with peaks in excess of 20 metres, and temperatures measured using some of our sensors at over 1500 degrees Celsius, which was enough to damage some of our research equipment, although thankfully we were still able to capture the data out of those damaged sensors despite the heating that had occurred. So the new purpose-designed instrumentation was successfully tested and utilised, and we were able to capture excellent data for the 2 different fuel types we've burned in so far. And from the results to date, they're showing that the new fire spread theory looks to be valid, at least in these 2 gorse and stubble fuels that we've burned in to date, but it looks very promising as we move forward. We've also been able to develop new analysis methods for fire spread rate and hot air parcel movement above the flame front from the video imagery. And these burn experiments are the first known attempts to quantify the turbulence generated by these flame fronts across all the different scales, from the background atmosphere to above the fire to within the flame front, using the specialist equipment we were able to obtain. And a new prototype fire spread model is currently under development that will be further testing using the data collected from the burn experiments. So the next steps are to move on to conducting burns in standing wilding conifers, and we have a site near Lake Pukaki in the Mackenzie Basin, where here we have 10 to 12 metre tall dense wilding stands, where we hope to now burn in 2021-2022. All of that was put into a state of turmoil recently with a fire late last month, but thankfully that missed our research blocks, and hopefully we can still burn in a year's time. All right, so the second project I want to talk about is the real-time fire tools. So here we're looking to develop an integrated tool suite that combines a series of separate tools for fire detection, fire spread and growth, and for the dispersal of smoke produced by the fire. So this system will be able to detect when a new fire has occurred, and from that location and the fuel types it's burning in, use the Prometheus fire growth model to predict how big the fire is, what's getting consumed in the way of fuels, and what's the rate of spread and of that fuel consumption, which then is input into the smoke model, which then predicts the emissions that are produced by the fire and how high the smoke is going and where downwind that fire is, that smoke is likely to end up. So a prototype web interface has been developed, and we're going to test the beta version of this integrated model over the coming fire season. So to date, we've been able to successfully develop the individual components and link them together. And now we want to test the full integrated suite over the coming fire season. And we're also in discussion with Fire and Emergency New Zealand regarding how we take this system forward and implement it operationally and use that information in real time to support fire decision making. So as I said, the system combines three different components. The fire detection component. So here, these are the satellite fire hotspot detections, in this case from the MODIS satellite, which are then used to generate fire spread from the Prometheus fire growth model, which in turn is then used to generate the smoke and where that smoke is likely to go. And so the interface also allows us to be able to download that information so that we can then overlay it over the likes of Google Earth imagery to show the fire spread in this case from the Prometheus model, but also the smoke. And we can animate that into a series of short video clips showing fire and smoke spread as well. All right, so the third area I want to talk about is the development of a fire alerting sensor to warn of the approach of fire. And this is a simple temperature measurement made via a thermocouple that's connected via a communications package that sends alerts when a temperature threshold is exceeded. So in this case, we've been using temperatures above 65 degrees Celsius. So this sensor sends the location and the temperature data, and the frequency of that sending of the data increases as the temperature increases. The system has been tested over satellite and radio communications, and it can be linked to the internet or made accessible via a smartphone application that alerts somebody monitoring that to a high temperature reading from one of the sensors. These sensors have been successfully trialled in our stubble research burns, but also in our more extreme Rakai Gorge Gorse burns this last year, where they showed the approach of a flame front and were able to survive the temperatures in excess of 1,000 degrees C when properly insulated. So the aim here is that the sensor can be used around the boundaries of a prescribed burn to indicate where there might have been a breach or escape, or they could be used as a quick deploy sensor within the forest, or dropped from the air above a fire to indicate the spread of a fire as well. We've also been able to link the sensor to the operation of fire suppression systems, and in this case to automatically switch on a sprinkler when the threshold temperature was exceeded. And here it was able to turn on the sprinkler via both electric water valves if the pump was already running, or if you had an electric start pump by switching on the pump itself. And we successfully demonstrated the use of the sensor in this way at a workshop that we held in Northland in August last year. Work's also investigating use of a modified sensor to monitor the internal temperature within skid site piles. And here the aim is to reduce the occurrence of costly spontaneous combustion fires by monitoring pile temperature remotely and providing an alert when, again, a threshold temperature is reached. And that links to some other work that we're doing within the program and for Fire and Emergency New Zealand around the factors contributing to the occurrence of skid site fires. And the report is due on that very soon. I just want to finish by highlighting some of the tech transfer mechanisms we're using to get this information out. So hopefully you're aware of the research weblog that's now been running since June 2018. You can subscribe to the weblog via the Rural Fire Research website. And here we provide brief updates on research activities and new publications, etc. But also to the new YouTube video channel that we've created. So if you go to YouTube and search Rural Fire Research, you'll find the channel there. And here we have a selection of videos from research burns, other research activities and presentations. And to date, we have around 24 videos uploaded for viewing. So thank you very much for the opportunity to update you on the progress of the Rural Fire Research and of the Extreme Fire program in particular. Now, if you want more information, you can get information from the Rural Fire Research website, which is, the link is listed here, and also through a link from the Forest Growers Research website as well.